We are Graphilica, and today we're going to present to you a novel approach to scale production of graphene. My name is Mohammed AlBaity.
And I'm Abdullah AlMansur.
I'm Faris AlShuaibi.
And I'm Mandil Sibakoti.
And our mentor is Ries. Graphene. This word is so new that spell check in your computer does not know it yet. What is graphene? Graphene is a 2D layer of carbon atoms arranged in a regular hexagonal pattern, connected by covalent bonds. Graphene was known since 1916, but its first isolation was in 2004 by Professors Andre and Kosaya in the University of Manchester, where they won the Nobel Prize in Physics in 2010 for their pioneering work. Graphene has many unique properties. One of these properties are it's an excellent conductor of heat and electricity. It is almost transparent, and it has the highest tensile strength of any material exists today. There are many ways to produce graphene. One of these ways is the chemical vapor deposition, which we used in our process. Also, there's exfoliation and the hydrothermal self-assembly. Graphene has attracted many industries due to its broad applications, such as touch screens and transistors, conductive coatings and ink, and solar cells. For this project, we had three main objectives. Number one is to scale up graphene silicon dioxide composite using a novel continuous CVD process to produce touch screens. Number two is to make graphene more accessible for commercial and industrial applications. And number three is to lower the cost of producing graphene while maintaining the high quality of graphene layer. And in order to achieve our goals, we used a roll-to-roll concentric tube CVD reactor, a patent that was developed by researchers from MIT and University of Michigan.
Graphene market is projected to reach 149.1 million in 2020 with a 44% annual growth rate, as there is a new kind of demand for graphene every day. The global transparent conductive screen market is expecting a huge demand, with the key providers in it, such as Samsung and 3M and Corning, heading toward more graphene-based touchscreen technology. Indeed, indium tin oxide holds 97% of global transparent film market, and graphene is proven to be superior to indium tin oxide in its conductive properties. Samsung showed a huge interest in graphene as they filed a number of patents, a number of graphene-related patents, and they need around 7.8 billion centimeters squared to only equip 30% of their annually produced 336 devices. We will be able to cover that by having. We will be able to cover that through. We will be able to cover 1% of that through our production rate. It is also important to notice that the current prices for graphene are around $60 to $80 as provided by Graphene and other companies such as ACS Materials, and it's a lower product quality than the one produced by our process. Our price was around $0.2 per centimeter squared, which is a competitive price to that of the ITO of 0.187, and we will show you in the couple next slides how we were able to get to that price.
Here's a process flow diagram of our system. So the copper foil is wrapped around the inner tube of the CVD reactor, and ethylene and hydrogen gases enter the system, and in the presence of high temperature, the graphene layer form on the copper. Then the copper graphene layer goes to a transfer step where the graphene transfer from the copper foil to a silicon dioxide. After that, the product goes through a couple of characterization tests, and if it passes, then we get our final product. Also, one thing to mention is we added a recycle stream to our process, which to recycle the unused gas in our process, which Faris is going to talk about in more detail. And here's the design of our CVD reactor. So the uniqueness and significance of this design centers around the concentric tube. By adding an inner tube to the existing tube, they were able to reduce the amount of gas used by 90%. So basically, you can either enter the whole volume of the gas to your system, or reducing it by adding the other tube. So you have a smaller volume here, which is the confined volume between the inner and the outer tube. Also, in this reactor, we have two zones, which are the annealing zone and the growth zone, which I'm going to talk about in the next slide. And another unique feature about this process is that it operates at an atmospheric pressure, which is different from other processes which operate at higher pressure. And this is the reaction that takes place in the CVD reactor, which is the ethylene reacts with the hydrogen to get the graphene and the methane gas and the hydrogen. And the growth rate of this graphene layer forming on the copper foil was found to be 25 millimeter per minute. And this growth rate was found to be the optimal growth rate for a uniform graphene.
So, as Mohammed said in the previous slides, we'll be recycling some of the gases. The unconsumed helium and hydrogen will be recycled after it leaves the reactor, and then as it goes to the gas separator, the helium will be pushed back to the inlet, and the hydrogen will leave the gas separator from the top stream. Then the hydrogen will move into the ratio control, which will split it into two streams. The first stream, which will consist of 55% of the hydrogen, will go into the inner tube of the CVD reactor, while the rest, which is the 45%, will move to the outer tube. So the recovery efficiency of our process is estimated to be 98%. The recycle ratio is 98% for helium. Since helium is introduced in our process as an inert and it doesn't basically be consumed in the process. For hydrogen, the recycle ratio is 96.4. The 1.6% is basically consumed within the reactor. We're estimating to save $16 million annually on raw materials with this recycle. So, in order to meet our target production for our company, we decided to go with three CVD machines, and basically a production rate of 7.7 square meters per day. In order to achieve that, we focus on three main criteria for scaling up. First was the reactor design. We have picked out a specific reactor from Thermal Product Solutions with specific dimensions and specific specifications for the performance. Additionally, the second criteria was the inlet fluids and raw materials. For the gases used, we had to scale them up using Reynolds number, such as for the helium and hydrogen. For the final criteria, which is the output dimensions, which is the dimensions of the copper substrate leaving the reactor, it will be leaving the system at a rate of 25 millimeters per minute, and the thickness is estimated to be 51 micrometers, while the width is almost 9 inches.
After graphene on copper layer leaves the reaction furnace, it needs to be transferred to an SiO2 layer to be used in touch screens. It is the longest part of our process. The idea is pretty simple. As we place the graphene on copper layer in a 50 gram per milliliter iron nitrate solution and wait for the graphene layer to be etched to the surface of the iron nitrate. After we carefully remove the copper layer and then place an SiO2 layer for the graphene to be deposited on it. We were able to speed up that process by having stacked trays of iron nitrate solution, and that enabled us to get to save space and time and get to our production rate of 76 million centimeters squared yearly. A perfectly deposited graphene layer consists of a number of carbon atoms. Each carbon atom is connected to 3 other carbon atoms. This structure will allow for the 6th valence electron of carbon to be there for conduction, and it showed an ideal Ig to I2D ratio of 2. Through our process, we were able to get to an Ig to I2D ratio of 1.57, whereas the current products provided in the market has a ratio of 0.7. We also use an FESAM secondary electron imaging to make sure that we have a better quality product.
Okay. So in the tube furnace, there are a various range of temperature available from between 800 degrees Celsius to 1200 degrees Celsius. However, for our optimal reaction conditions, it's better to have it around 1000 to 1010 degrees Celsius. Thus, to regulate the temperature, we have a temperature controller, which is controlled by a feedback controller that contains a thermal controller and a temperature transmitter. Here, once we set the temperature at 1010 degrees Celsius, so once the temperature of the furnace goes above the set point, the valve over here closes so that the temperature comes down to the normal required temperature. In case if the temperature goes below, then the valve is opened to heat up the system to bring it back to the set point. Next, we have the substrate selection. So, like we mentioned before, we introduced copper into the tube furnace in order to form graphene on it. However, we had choices to choose between substrate materials. Some of them were copper, nickel, and aluminum. Among them, we chose copper because copper was less expensive than the other available materials. Also, copper and graphene composite form uniform and monolayer, and it has a low oxidation resistance and low binding energy. Our final product is not copper and graphene, but graphene in silicon dioxide, so we need to have substrate that's easy to remove. As you can see in the microscopic view, we have two different sheets. One is copper graphene and other is nickel graphene. Copper graphene is more smooth and monolayer, whereas nickel graphene is multi-layer and uniform. Hence, it's easier to extract copper out from graphene rather than nickel. Over there, we have a data of binding energy. The top one is of copper graphene and the bottom one is of nickel graphene. The binding energy of copper graphene is comparatively low than the nickel graphene, so it's easier to extract out graphene from copper rather than nickel, and easy to process to make it into silicon dioxide and graphene.
So for raw materials and consumables, first on the list is copper, which is the substrate I've just talked about. Silicon dioxide, which will be in our final product. Additionally, we have the gases will be entering our system. Most of the costs were consumed by helium and hydrogen, especially hydrogen, as it costs around $600,000, since our process must be overflown with excess hydrogen. For the consumables, iron nitrate will be used in the graphene transfer procedure, and chem wipes, acetone, isopropyl alcohol will all be used in the treatment of copper prior to entering the CVD reactor. So for our major equipment, here's a quick list. First is the tube furnace, which is the CVD reactor. We're using a single zone heating, which reaches up to 1200 Celsius degrees. Its cost is around $40,000. We have the gas separator. You could see it took a lot in terms of our installed capital cost. After we have done our calculations, the gas separator was proved to be beneficial and economically beneficial as well. So for the SEM and optical emission spectrometer, they'll both be used for the characterization of our final product. We have used a couple of controllers as well for the gas flow and temperature. We're using physical vapor deposition machine, which will do the electron beam evaporation on the copper substrate for coating. We're using quartz tube, so it sustains the heat of our CVD reactor. And finally, we're using a cold room to store our gas cylinders of hydrogen and helium.
Our plant will be located in India, as it will allow us to produce at a price competitive to that of the ITO, especially that we have found a ready-to-use industrial facility with an easy access to shipping facilities for $190,000.
Here we have a list of our manpower. In order to fulfill our production requirement, we plan to run our plant 24 hours a day for 330 days a year. So we decided to hire around 29 operators who will be responsible for doing all the necessary workings in the plant, such as recoiling the copper foil, performing the CVD reaction, as well as the graphene transfer, and finally stacking up the final product. Next, we have 3 technicians. Since we are running our plant for 24 hours, regular maintenance of tools are required. Any problems in our equipment can cause our production process to delay, which we do not want. Hence, the technicians will perform regular checks and safety checks. Finally, our process might have some alterations depending on the temperature and changes in the reaction. To monitor the constant reaction rates, we have decided to hire 3 engineers. And finally, we have 1 manager to supervise all of the employees and look after the plant. So our total expenditure on workers is around $420,000, which includes 25% tax plus insurance according to the government regulations in India. Here we have the utility consumption list. Since our plant is in India, the electricity consumption per unit is around $0.06 per kilowatt hour. Our plant runs totally on electricity. Among them, these are the key equipment mentioned before. The tube furnace has the highest consumption rate because we're heating the furnace at a temperature of around 1000 degrees Celsius. To heat that temperature using electricity consumes a lot of energy. And we have additional utilities that include air conditioning of the facility as well as normal appliances used by the employees. So here is our FMEA result. Based on our process, we discovered 4 key places where if the equipment goes wrong, then our process gets hampered. The first one is the gas flow controller. It's responsible for regulating the right concentration of gas into the tube furnace. In case if it malfunctions due to certain leakage of gas, then the concentration of gas going into the system decreases, which hampers our reaction rate and ultimately decreases our product quality. Next is the cooling fan. The substrate of copper and graphene formed in the tube furnace is at a temperature of 1000 degrees Celsius. So coming out of the furnace, the substrate is very hot. We want to reduce that temperature as low as possible because the substrate goes into the solution tank where iron nitrate solution is present. We do not want high heat entering the solution causing unfavorable reaction. Next is the thermal controller. Like I mentioned before, there's a set of temperature range that the tube furnace can obtain. If the temperature goes above the required temperature, then again the process is hampered and our product quality decreases. Finally, there's the solution tank where iron nitrate solution and silicon dioxide is present. The concentration required to react silicon dioxide with graphene, if not met with the right quantity, then the reaction and product quality can decrease. And again, based on our process, we discovered two hazardous nodes. The first one is again the gas flow controller. Like I said before, if there are leaks in the pipelines, then improper gas supply concentration goes into the tube furnace. Leaks of gas can cause severe consequences, and the technicians are responsible to make sure this does not occur. Hence, proper maintenance and watts on pipelines is necessary. The next node is the tube furnace. Like I mentioned before, there are various range of temperatures possible in the tube furnace. Especially we're dealing with flammable gases such as hydrogen and ethylene going into the furnace. Improper temperature range can cause flames to occur into the tube furnace. And in order to avoid such possible scenarios, it's better to have an emergency turn-off system in case the temperature exceeds the limit. Here we have MSDS of our chemicals used. Most of the chemicals are not harmful to people and the environment. However, some gases such as ethylene and hydrogen are highly flammable. For ethylene, we have, in case of ethylene leaks, we have ethylene scrubber to remove ethylene into the plant. Next, for hydrogen, we decided to install hydrogen sensors to notify us if there are any hydrogen leaks in the plant. Silicon dioxide and iron nitrate are slightly toxic chemicals. However, the employees are properly equipped with safety goggles and gloves.
We ask ourselves what effect graphene can have on the environment or the end user. We recycled the hydrogen and helium in our system, and the methane produced from ethylene was removed by bacteria in the exhaust pipes. Also, the excess ethylene will be consumed by the ethylene scrubber to burn ethylene and produce air. So these are like three solutions to make graphene composite more friendly to the environment. Besides that, graphene is one of the least toxic nanotechnology products.
So for the capital cost, initially we calculated the ISBL cost through the summation or addition of the equipment required for our process, in addition for the cost of the plant and facilities and the cost of the clean room. From that value, we were able to calculate the following OSBL and the other costs inquired. The total cost was estimated to be around $3.76 million. We're spending around $800,000 on engineering costs for engineering and procurement. So for our cash cost of production, it was estimated to be $2 million, with 2.64 for the cost of production, including the annual charges with a tax rate of 15%. Our revenue is estimated to be $50,240,000 with the price point of $0.2 per centimeter squared. Our gross profit is estimated to be around $13 million. The fixed cost was nearly high for chemical engineering processes, given that our process is more of a labor-intensive process. So for the project feasibility, it is estimated that we'll be able to pay back our investment in 4 months and 15 days. Our return on investment is almost 300%. For the depreciation method, we have used straight line depreciation. Our cost of capital was estimated to be 25%, given our investment is considered moderately risky. The corporate tax in India is 15%. And the graph below, you can see the net present value of our company in the first year. Basically, that's when we incurred the capital cost, and basically down to 20 years, well, our net present value will be around almost $30 million. I mean, so at the end, graphene, what significance would our project have? I mean, first, we have the environmental impact. Graphene is 100% recyclable. Graphene will help us reduce the energy consumption, as there have been research on basically using graphene for solar cells within the mobiles. Additionally, we have additionally we'll be able to substitute the rare metals, as Abdullah said. ITO basically consumes a lot of iridium, and iridium is a rare metal nowadays. So basically, graphene will be used to replace that. I mean, for business impact, the most obvious one is basically higher sales for companies as their product develop and progress. More people will be inclined to buy them. Additionally, graphene will help push back the previous limitations and drawbacks of certain technologies, given the features it has. So basically, further innovation and development of products. For individual impact, with graphene, people will be able to charge their phone way faster. And there have been some development in the mobile healthcare industry using graphene touchscreens.
So for future work, we're planning to spend more money on R&D to recycle the copper foil that was used in the system, and also reduce the amount of time spent for graphene transfer, since it takes about 24 hours. Also, we're planning to expand our market share and produce other graphene products. And at the end, we want to acknowledge these individuals who helped us throughout this semester. Professor Webster and Professor ChE guided us throughout this semester, and Mr. Peter, our mentor, and Professor Abdullah Murphy. She provided us with articles to improve our process, and Professor Marlene Miles from the Mechanical Engineering Department helped us to understand the process more. Thank you very much. Any questions?
We have time for questions this time.
Yes. Can you go back to the copper transfer slide? We were talking about transferring graphene onto silicon oxide.
Yes.
This was also from the guys at MIT, or like where is this?
Yeah, it was from the guys of MIT.
Yeah. Just the design of this tank was.
And then,
it's our.
how thick of graphene are you expecting to grow in copper?
What is that?
How thick of graphene film are you expecting?
Yeah, it's in nanometers. I think it's 1.58 nanometers. It's really thin.
It's really, yeah.
And they show that you can get a good uniform transfer from one.
Yeah, I mean, yeah. Basically, we'll use the SEM testing to perfect it. I mean, usually in terms of processes, the average was around from 90% to 95%. We estimated that we'll be able to have a 93.5%.
And if you use the the specification in the design, and at 25 millimeter per minute, it was proved that it's going to give you a uniform graphene layer on the.
Yeah, even the
on the
temperature
copper.
level. Yeah.
Also, the product quality is usually characterized by the ID to I2G ratio, and through this process, we're able to get a good ID to I2G ratio.
Well, if you're getting a 25 millimeter per minute growth rate, then you have to be doing that for like a fraction of a second to get nanometers.
Yeah. I mean, yeah, it should take a small amount to be produced.
And then is that etching solution going to be compatible with like cell phone? Because you're going to have all the other electronics on there, and then you're going to have transfer.
It's going to be rinsed after the rinsed and cleaned after. So, and
I have a related question. At the end, you said possible future improvement is to recycle the copper foil.
Yep.
Can you tell us something about the problems that need to be solved in order to do that?
So, because we're not sure how the waste in the foil after we remove the graphene, it's going to be removed, to reuse 100% of the copper.
and it could affect the quality of the surface if we use the
Yeah,
copper
and we
more
need to
than
spend more money to see. We didn't look at that until at the end of our project, so we want to take that into consideration in the future.
Yeah, I mean, we have honestly just recently considered that, and as Mohammed said, we don't know honestly the implications of what would happen to the copper, and you cannot risk the quality of the product, since quality is the top priority for graphene manufacturers at this point.
I have questions, but are there any others from any students here that are watching? All right, One question I heard was your control system for your oven or your temperature controller. And so that's on the slide, and I can't see it from my angle well, so just stand back a little bit so I can study this one to see if I'm missing something. Right there, back, that one. So you say when the temperature is low, you would increase flow? And if your temperature...
No, operate the,
What's the F gas? What is the F gas?
That's the helium and
That's the helium?
the helium.
Well, that's the helium.
Yeah. You have the helium and the hydrogen entering the system.
So if temperature is 990 Celsius, what's the system supposed to do?
No, so if it's what? Can you repeat that? If it's higher than...
So if the set point's low,
Mhm.
is the valve supposed to open or close?
No, that you can increase using the control, I mean the machine itself. You can increase the temperature.
Temperature with the machine.
Yeah.
And then if it's hot, you would...
You would close the system. We would close the valve, so the hydrogen does not go into the system and react.
You
Because
would
it's-
close the valve,
Yeah.
so you wouldn't have any reaction.
Yes.
Yeah, I mean, if you could go to the equipment list, there's the thermal control included. It's used for that specific model of CVD we're using. So basically, I mean, the reactor itself has the thermocouple, and from that we'll be able to basically change the energy going to the CVD reactor or leaving the, yeah, that's the one.
yeah, we have temperature controller and transmitter setter that both
All right, I'm gonna
operate.
get stuck. I'm curious, you showed a Raman spectrum. What was the source for that?
That's that might.
Very early in your presentation.
For characterization.
Yeah, that,
Right
that,
there. So what was the source for that? Is that your work or
No, that's the
No.
Professor work or?
It's
the
from
MIT.
the...
research.
MIT.
Oh, it's from the MIT?
Yeah.
Yeah, the patent had spectroscopy
Or from the
results.
patent or whatever?
Yeah.
So it might have been helpful to put that on there as a citation. Okay.
Any other questions?
Yeah, I got them. So you're gonna work in India. One of you must be from India, right?
No.
None of you are from India?
I'm close by, I'm from
You're
Nepal.
close by, huh?
Yeah.
But I was thinking, you know, there's a movie going back called Back to School, featuring Rodney Dangerfield, and the business professor gets up and talks about all of these things. And then Rodney's laughing, saying, you didn't think about having to pay off the waste collector, the union. And in India, I understand, you have to pay off people. I'm just wondering, how would you factor that in, and what? Did you put in a number for what's called contingency?
Yeah, a little, like in the numbers we put in in our manpower, so we basically like rounded that off to the nearest million. So like whatever
For the
value.
wages, yeah.
So we rounded that off to the nearest million rather than the thousand.
But is there, on your plant cost, did you have any?
Yeah, we had the contingency cost, but I mean, it wasn't.
Was there a contingency yet?
Yeah, yeah, but I mean, it was almost 10%, which aligns with the.
Almost, it's gonna have to be 10, I mean, even in the United States, they're.
Yeah, I mean, yeah, that's exactly my point. Like, we did it based on the United States, honestly, contingency cost rather than the Indian contingency cost.
That caught my interest when I was listening.
Yeah, I mean,
Is the salary correct?
yeah, I mean, yeah, I was planning to say that we're paying them actually more than the average.
Yeah, average,
Salary.
well, labor cost in India is from $2 to $5 an hour.
Okay,
Yeah, operators are usually paid too.
all right. Well, you guys may not know this, but I am impressed. Really a nice job.
Thank you.
Thank you.
So,